Continuing with our polyprotic acids, this last section is called Calculating with Polyprotics, and I don't want you to get the wrong idea. I said in the first video you're not going to actually be doing math. With chapter 11, we're not going to be doing the intense math with this, but you will see some calculations that are repeated that we've already learned from a previous acid-base chapter. And I'm not actually going to review with you those calculations because it's all part of this acid-base stuff that you're still working on. So it's kind of the idea behind the calculations is what we're going to be focused on here. So when I have a diprotic acid, I've got something that, well, there's like this intermediate form, the middle form, okay? Because there's the thing that has both protons, the diprotic acid, and then it can lose one proton, so that's like option 1. And then option 2 is when it's lost one proton, and then option 3 is when it's lost all 3 of them, okay? And we looked at the Ka1, Ka2, Ka3 values as needed. For this one, there'd be 2 Ka values because there's 2 protons. So going from 2 protons to 1 proton to 0 protons here. And we can see that big difference between Ka1 and Ka2. Our textbook, apparently it's too much work to write A, so they just turned to calling these K1 and K2 instead of Ka1 and Ka2. So I followed that notation because that's what our textbook did. So if we were trying to solve for the pH of this diprotic acid, so of this, okay, I've shown you that we have 2 equilibrium equations here, right? Well, and H3O plus is in both of them. The good news is with a diprotic acid, as long as it's the chemical you're starting with is in that acidic form, where it's got all the protons, still has all its protons. When we calculate the pH, we can treat this like a monoprotic acid, which means we can do one ice table using Ka1 only. So polyprotic acids, if the acid we're starting with is in its most acidic form, it has all of its protons, treat it like a monoprotic acid. Do an ice table, kind of like that HA plus H2O, equilibrium H3O plus and A minus, like that, only it's just gonna so happen that it has more than one proton. So you still could end up having to use the quadratic formula or not, depending on the value of the Ka. So in this case, you would have to use the quadratic formula because it's -3, so it's too large. But we can just treat it like we would any old weak acid. Great news. We already know how to do that. Okay. So that's what I'm pretty much, and the reason why, I guess the background behind that is Ka2 is going to be so small that means that second equilibrium step does not happen readily enough to contribute to the pH. So the first equilibrium step is the one that contributes to the pH the most, so we're only going to calculate using that one. So a solution of a diprotic acid behaves like a solution of a monoprotic acid, where you treat Ka1 like just Ka, just ice table. So one ice table using Ka1 only. No Ka2. Okay, awesome. We can do that. The basic form, the form where it has no protons, it's just a base, okay, at that point. Well, the fully basic form, the one that's lost, so no protons, it has no protons. Although it can accept 2 hydrogens, the Kb form, the first hydrogen it accepts, is significantly larger than the Kb2. So, following the same trend, something that is a polyprotic base, but it's in its fully basic form, so it has no protons. Just treat it like a monobasic, so treat it like a B. Just do ice table with Kb1 only. You can ignore the second step, so we're ignoring that step. We're just doing one ice table using this. So like with the acidic form, we were ignoring the second step, we were just doing one ice table with that. Okay. So again, you've done calculations like this before with a weak base only or a weak acid only. So the good news, if it's polyprotic and it's in its most basic form, treat it like a weak base. If it's in its most acidic form, treat it like a weak acid. We know how to do that. So that leaves us with, what are we going to do with the thing in the middle? The intermediate form, the one where it's lost one proton, still has one that it could give away, meaning it's lost one proton. So it could donate the proton it has left, or it could accept a proton. In other words, it could be an acid or a base. Okay, so in its intermediate form, it's not fully acidic or fully basic. It could be either way. I'm not going to go through the whole background on this. This is just showing for that intermediate form what it looks like when it acts as a base and what it looks like when it acts as an acid. So the calculation for the intermediate form, it looks like it might be brutal because you might have to do 2 ice tables. But good news is it turns out that the intermediate form is mostly independent of concentration, meaning whatever the molarity is of the intermediate form, it doesn't really impact the pH. But we can calculate the pH of a solution that's in its intermediate form by taking 1/2 of the pK1 plus pK2. So all you have to know are the pKa and pKb values. Okay, so the good news is no ice table for this. So the intermediate form, you would have to use this equation. Okay, and so whatever the molarity is, it might say it's a 0.0500 molarity. Nowhere in that equation does it use the molarity, and I'm telling you that's fine. It's almost independent of concentration, so as far as we're concerned, we're not worrying about the concentration. So I guess I lied. There is one new calculation in this chapter that you'll have to do, and that's that one. This equation would be given to you, so you would just have to know when to follow it. If you want to know how they got all the way to the point where they believe that equation, that's what these page numbers are for. I'm not going to test you on the conceptual side inside of it. So that was how we could do the calculations. More of the conceptual side of this is if we've got a polyprotic acid, we've just talked about how it has, if it's diprotic, 3 forms, right? The fully acidic form, it has both of its protons. The fully basic form, it has none of its protons. And the intermediate form, where it has 1, and it could either serve as an acid or a base. So since we're not going to do, any fancy calculations with this, one thing that I do want us to understand is based on the pKa and pKb values, pKa1, pKa2, pKb1, pKb2, how we could determine for a species, for a chemical, at a given pH, which form is the most predominant form? Which form is there the most of? Is there the most of the fully acidic? Is there the most of the fully basic? Or is there the most of the intermediate? We're not really mathing. We're just deciding at a certain pH which one is there the most of. So for a monoprotic acid, this is how we could do that. So monoprotic, just HA. So whatever the pKa value of the acid is, if the pH in the situation is more acidic than the pKa, then the predominant form, the version that there's the most of, is the HA. If the pH in a situation is more basic, so this would actually be, so I said more acidic, which means lower pH, and this is higher pH, right? More basic is a higher pH. If the pH is greater than the pKa, it's more basic than the pKa, then the base form is more predominant. So remember, every weak acid has a conjugate base. So there's the weak acid, and there its conjugate weak base form. Okay, so if you know the pKa of the acid and you know the pH of the situation, so I would have to tell you what the pKa value was and say, oh, let's say that this chemical, the pKa is 4.20. And I've got a mixture of that weak acid, just mixed with water. Okay, that beaker has a pH of 6.3. Which version is there more of, HA or A minus? Well, if the pKa value is 4.20, 6.3 is more basic than that. So there is more, not wanting me to write, more A minus at that point. The base version, there is more of that. That's how we'd handle it for a monoprotic acid. Okay, so diprotic and like triprotic, it works pretty similarly. It just turns out that there's more than 2 forms. There's 3 or 4 forms. So this graph is just showing us the fraction of the 3 forms that are present at any situation. So this would be the most acidic form, has all of its protons. This is the most basic form, has none of its protons. And there's the intermediate form. So we can see at certain pHs, this one is the most of, and then at certain pHs, we have the most of this chemical, and at certain pHs, we have the most of this chemical. And those dividing lines are related to the pK values. So let's see a picture just like the last one. So this is for a diprotic. So pKa1 and pKa2 are the lines. So let's say the pKa1 for this chemical is 4.92 and the pKa2 is 8.36. Okay, And I'm telling you that my beaker that contains this chemical, contains H2A, has a pH of 3.6. Okay, so 3.6 is right here on the scale, right? It's more acidic than 4.2. So that means at a pH of 3.6, there's the most of H2A. That's the chemical there's the most of. At a pH of 6.93, well, 6.93 along our number scale kind of falls here-ish, right? It's greater than 4.92 and less than 8.36. So that means at that pH, the one that there's the most of is the intermediate form. So if the pH was 10.64, that falls over here. So there's the most of a -2. Okay. If we've got a triprotic, we see a similar thing. It's just pKa1, pKa2, pKa3. But for me, this little number line thing is what helps it make sense. So if you were to be given the pKa1 and pKa2 values and asked what form is predominant at a specific pH, I would expect that you could tell me that. Now the math, the stuff that we're not doing that goes along with chapter 11 is calculating in what fraction, how much of it is the intermediate form versus the acidic form versus the basic form. You're just telling me which one there is the most of. We're not going to figure out how much of it there is compared to the others. That's the math that we're skipping out on. Okay. So while we're talking about polyprotic acids, just a reminder, we talked about this with the other acid-base titration, or the acid-base titration chapter, but polyprotic acid titrations have differences in their titration curves because we have more than one pKa, so we see more than one equilibrium or equivalence point, one for each pK value. Okay. Now, they are not as obvious as they are with the monoprotic acids and bases with their titration curves. Those jumps and drops were super obvious. And it's not nearly as obvious for these. For diprotic, it's a lot more obvious. So like diprotic acid, that like there and here. But either way, there's some of them are just kind of real vague. And that's because they're weaker acids. Their Ka and Kb values are smaller. So with polyprotic acids, we had the Henderson-Hasselbalch equation. So when we're dealing with buffers and we're dealing with polyprotic acids and bases with buffers, we technically have the Henderson-Hasselbalch equation that relates to the polyprotic acids, one that takes into account pKa1 and one that takes into account pKa2. What I did in chapter 9 with the buffers was I just always gave you the correct pK value that was appropriate for the chemicals. So you don't really need to memorize this, but just pointing out that depending on the versions of the polyprotic acid chemical that you've made your buffer out of, you might be using pKa1 or pKa2. Again, I just promised to give you the version that's appropriate in the situation. So that's as far as we're going in chapter 11. Again, the stuff that we're not doing that's in the chapter are calculating those fractions of the species, how much of each type of chemical is present at a certain pH. We're just choosing which one there is the most of.